Natural Resources class. Here we go with Mineral Resources video lecture number 2. We left off discussing fossil fuels, coal, crude oil, natural gas, and peat last time. We're going to look in a little more detail at them, at some of them. And so as we do that, and in light of a desire for full disclosure, I want you to know that that my wife and I do own an oil well. Yeah, we're not rich. It's not earned. Haven't received a check from it. My father-in-law, a very kind, humble farmer from western Kansas, hard worker, successful, not wanting to incur a major inheritance tax issue, gave each of his 5 children a half section of land. And my wife and I got this half section, and it has a center pivot irrigation system on it, and it has an oil well on it. So in addition to being a geology instructor at Bethel, I also have firsthand knowledge in that regard of the oil industry. So I wanted you just to be aware of where I'm coming from. We're going to be dealing with fossil fuels again, as I said. Generally, if you look in your notes, there's a general statement where you have burial of sediment, whether it is terrestrial or marine, that basically seals off oxygen. So not every kind of sediment will do this, but in the right environment, the sediment, if it's small enough, typically silt or clay-sized sediment, remember those are very small particles, will deprive oxygen of the dead plant material here or here that remains, and cause further decay, complete decay to occur. It'll keep it will keep complete decay from occurring, and so it'll short circuit it. If that sediment, the plant or animal sediment, gets buried with the right kind of clay. It has to be the right type of clay which will act as a catalyst. A catalyst speeds up a reaction, helps it to go faster. So that has to occur. There has to be the right temperature, and so with deep burial of this sediment comes pressure, and with pressure comes temperature, and so that temperature is also required. And then you've got to have enough time to get fossil fuel to form. If you start off with marine sediment, like in this lower image right here, and you bury it with the right kind of sediment, you will have to have also the right type of clay and the right conditions. My dog just came running in here all wet, trying to step on everything, so pardon me. And where was that? Marine sediment, the right kind of clay, and the right temperature, 50 to 100 degrees Celsius, you'll get crude oil forming. And again, if you remember what crude oil looks like, here's a gentleman holding some, and that is pretty accurate. It looks like it smells like a mixture of engine oil, gasoline, diesel, everything mixed together, which it is. From this basic product, all those products are derived in what's called a fractioning tower. Well, that'll be a topic for another day. So from this basic substance, we derive all the different fossil fuel products that we're interested in. Okay, so if it's the right temperature, you get crude oil. If it's a little bit higher temperature, over 100 degrees Celsius, you get natural gas forming. And so that's why in the Deepwater Horizon, the gas, being less dense, commonly forms on top of the crude oil. I'll show you that here. So this is what it looks like. This is what it was like. This is terrestrial, but if this were under the Gulf of Mexico, the Deepwater Horizon punctured through here, and they knew the environment was unstable. It wasn't the right place to drill for oil. If we were to use this analogy here, it would have been better if they would have gone over here and drilled. They got a big bubble of gas boiling through the surface, basically blew its way through the surface, ignited, and blew up that drill rig. So gas will form on the top. That's why you have what are called gushers, why the drill rig will drill a hole and the oil will come rocketing out. That's if there's gas mixed with the oil. There isn't always gas mixed with the oil, but there can be. Okay, so that's what you need in place, the conditions you need to get crude oil. but that's just going to get you crude oil. That's going to allow you to make it. If there is the right conditions, it'll form. But if this overlying rock cracks, as rock often will, as tectonic shifts constantly shifts Earth's surface, then the oil and gas deposits will simply seep to the surface, like I mentioned, people reporting in the 17 and 1800s off the coast of California, and evaporate away. If you leave crude oil at the surface, it will evaporate off its lighter components and just turn into tar. Again, to make the case that California is very rich in fossil fuels, if we go here to downtown California, this is a place I suspect you all have heard of. This is the La Brea tar pits. And here you have that thick, sludgy tar overlain by some water. And historically, animals would come to drink. Some would fall in, be captured in the tar, and die. And so this is a wonderful fossil bed for fossils of animals that were captured in that tar. So if we zoom out here, you can see where this actually is. The La Brea tar pits is right alongside Wilshire Boulevard in downtown LA. So let's see if it will name it for us. I wanted it to say Wilshire Boulevard. There it is, Wilshire Boulevard. And we'll zoom out all the way. And you can see you're in downtown LA. And that is an area where that crude oil that is abundant in California came to the surface, and the lighter stuff simply evaporated away, and you're left with these tar pits. So how do you get crude oil captured and concentrated in a reservoir big enough to justify oil exploration? Well, you need what's called a trap. Okay, and a trap, there are some images of different types of traps. These are not the only kind of traps, but this is some types of traps. The first one here is called an anticline trap, anticline-syncline. If you could picture the Earth's surface being pushed horizontally, one piece of Earth's surface pushed into the other, it would make a wrinkle. Let's see, I think I've got another image down below here. Yeah. Here's a wrinkle in Earth's surface, and the top of it we call an anticline, the bottom of it, so here's an anticline, down here it's called a syncline. So some places you'll find this called an anticline-syncline trap. But here this cap rock is impermeable to oil. The oil and gas can't break through it because it's a solid seal on that particular field of oil and gas. Okay, and so it can't break through it. And furthermore, because plate movement has made a high spot in the cap, the oil and gas accumulates right here in this spot. So if this whole layer called a reservoir rock below it will contribute gas and oil, which will slowly seep to this spot as it is formed. And so that's an anticline-syncline trap. Here you can see that reservoir rock a little bit more distinctly. And that's a wonderful place for oil and gas to be found. There are faults that displace rock and create a trap. That's what we have here. A stratigraphic trap here, because of the formation of different layers at different angles, can create a trap. This one right here is a salt dome trap. This is common in Louisiana, Texas. Actually, all around the world you'll find salt domes. But salt, if put under sufficient pressure, actually begins to flow. And if it can find a crack in an overlying rock, it will flow up through that. So you can find layers of earth that have a large contingent of salt in some deep rock layers, and that salt will accumulate and bulge up in an area. And if it's sufficient, it can cause a bulging of the overlying layers as well. And so what happens? Well, oil and gas accumulates right alongside it. Now, I'm going to attach to Moodle a video clip at this point of the goings-on, if you will, of the area around Lake Penour in southern Louisiana. That particular area had a salt mine that was exploiting the salt here, and an oil drilling rig that was trying to get oil and gas out of a very nearby location. And this is an instance of very real disaster, and I think you'll find it absolutely jaw-dropping what happened there. But again, we've learned from those mistakes, and yeah, well, I guess I would say enjoy the video. It's interesting. Not the best quality, but I think you'll find it interesting. So we've got these different kinds of traps. So as I say, oil will migrate from a source rock where it was produced to a reservoir rock, and there has to be a trap then, a seal rock, that captures it underneath that reservoir rock and concentrates it in an area that makes it exploitable, if you will, by humanity looking for that particular resource. If you think about why gas and oil is so sought after, it's the fact that there's a lot of energy contained in a small quantity of substance with the case of gas and oil. If you take wood, for instance, use it as a comparison, you got to cut, dry, and burn a lot more wood than you do coal, oil, or gas to get the same amount of energy out of it. So we are truly blessed as a country when it comes to natural resources, and this is just another example. Okay, so further, there's a couple of other associated resources with crude oil. Our country, it is thought, has 2 to 5 trillion barrels of sort of pre-crude oil trapped in what's called an oil shale. For instance, the Green River Basin in Wyoming has a lot of this kind of rock. And trapped inside of this rock is, a substance called kerogen. And kerogen is a precursor to crude oil. It will convert to bitumen, which looks like this. It's kind of a solid tar. And then bitumen will become crude oil in the right type of an environment. You got to understand something. Venezuela, that very traumatized, turbulent country, maybe more crude oil resources than even Saudi Arabia. Yet its population starves because it was under a socialist dictator named Hugo Chavez. And now he's gone, but the replacement hasn't been a great deal better for those poor people. They are blessed with phenomenal crude oil resources if they could intelligently use them. And I say they're going to intelligently use them if they're given the ability to, if they would have the political system that would allow them to do that. They have a lot of this kind of a resource as well, this bitumen. And so when Venezuela talks about its resources of fossil fuels, sometimes it's tricky getting them to admit, are you talking about bitumen, which takes a lot more refining to get gas and diesel out of, or are you talking about crude oil? But anyway, that's what the deal is there. So those are other closely associated resources to crude oil. So let's get down to it. Some of the big questions. Crude oil. How much do we have, and how soon are we going to run out? Well, this is from my older brother's textbook from college from 1971 that sought to address such a question. And in 1971, if you look here, the world supply of petroleum, let's go with that, was estimated to be 1 to 200 years. But in the United States, we were going to run out in 20 to 35 years. Well, 35 years from 1971 puts us at 2006, if my math is right. And I don't think we ran out. And in fact, we didn't even run low yet. So it makes you wonder what this number is like. Well, let's look at some other, I think, interesting facts. If I was to ask the class, do we import more oil or do we produce more domestically in this country? I would bet that most of you would look at a diagram like this and think this is what you'd heard most of. Domestic production declines, is on the decline. Import of crude oil is increasing, and that's the way she goes. Well, I want to show you another image. Actually, I gotta go back here. This one right here. So that previous image stops at 2003. Okay. So if we go here to 2008, 2009, in fact, it's gotten worse. Okay. And if you remember, 2008 is the big. That was during the mortgage-backed security crisis, the big recession, stock market plunge, all that. First part of Obama's administration, okay, if you remember that time. Look at what happened. Just before that, imports 63% of total, 60% of total. Well, let's zoom ahead a little bit. So we got through the bad times. Yeah, we imported a lot. We were producing quite a bit domestically, but less so if you remember that chart. So let's zoom ahead now to 2014 and 2015. And oh my word, what am I going to say about this? March of 2015, look at that. No longer 63% of our total crude oil use is imports. Now it's down to 42%, and our domestic production is 13.54. I think it's that million barrels, trillion barrels. I'm not sure which, but 58%. So if we go back here. If you look at the total production, here in August 2009, it was 19.72 million barrels. I think it's million barrels, I'm right. And here, we're up to 23.3 million barrels. Not only are we producing more domestically, but we're producing more in total. And so, why? Where is it coming from? Well, about that time is when this, along with other fields, really began contributing to our domestic production. This is the Bakken field. It's in what's called the Williston Basin. Okay, this is a sedimentary rock feature that contains gas and oil, and this was deep oil and it was tight gas and oil. That meant it was held tightly in small cracks in layers of sedimentary rock. If you drilled a traditional well there, it didn't really produce much because the cracks were unable to yield to provide their oil to that wellhead. Along came a process called fracking. And fracking drills a well, drills a hole in the ground, and it, let's see, I think I've got an image here. I'm going to pause for just a second. Okay, this is an image of fracking, what's going on here. So here's your traditional kind of well. Let's see if I go. Maybe I don't. Yeah, here we go. Traditional kind of well. Okay, so they're going to drill a vertical well. But the difference is with fracking is, well, there's two things. They're going to drill this vertical well. There's also the technology called horizontal drilling, which is not the same as fracking. That's a different issue. But basically, they can turn a drill bit. So from this one wellhead or pumping or drilling rig, they can turn the drill and go this way. They can turn the drill in this way. They get 360 degrees. So you require less drill rigs and less holes in the ground to explore a whole area with this new horizontal drilling technology. So along with that comes fracking. Okay, and fracking, so once they drill the hole, they'll send a charge down here, and they'll actually seal a part, and they'll perforate the pipe. They'll blow it and explode a charge. It will go through the side of the well casing, it's a hollow pipe, and into the rock around it and create these fractures. They'll then pump fracking fluid in there, which is water and what are called proppants, kind of like stuffing sand in those cracks to hold them open so that the oil and gas can flow past that into the well and up to pump. And they'll frack several zones here, and that's fracking. And of course, the big concern is that they contaminate the water table. Well, water tables are usually within a couple hundred feet of the surface, and they're down here 1.5 miles. You know, it was an issue in the past, that you could get gas seeping up around the side of the well casing and contaminate water. They now seal that off, and I'll try to include a video clip. And this is from the industry, so you have to understand their perspective. They're sealing that off now and making this a safer technology. So that's what fracking is. That's what fracking does, and that's what allowed the Bakken to be exploited and produce so much oil. If you go through the Bakken right now, I actually have a nephew that is working in the Bakken, and this is what it looks like. This is all brand new. This is an old traditional skipjack pump, and this is a new pump. Actually, I think I can zoom in on these a little bit. Yeah, and so these are all tanks, and this is the sad thing here. They flare off natural gas. In other words, they're just burning off natural gas because it's more difficult to actually capture that gas, separate it from the oil, and pump it to a tank than it is to just flare it off. And this is happening less often now because it's a waste, but it is still happening. Another way that this can be handled is, where did I have it? I have an image here of, here, a new well, and what they do in this well, they capture the gas in a tank right here. That natural gas then runs this engine which runs the pump. It's kind of a self-sustaining thing, and the oil pumped out of here goes underneath this field to a holding tank that's then trucked away to a refinery. But that's kind of a neat way to capture and utilize the natural gas to actually run the pumping operation. Doesn't always happen, but that's one thing. So this is what the Bakken looks like, and it's made a lot of very rich farmers in that part of the country from the oil that has been extracted from there. Remember from this previous image that I showed you, there's the Bakken. The Marcellus Shale, this is a national. Now the Bakken produces gas and oil. The Marcellus is mostly natural gas. But down here is the Barnett, and this is the Eagle Ford. One of these two is the Eagle Ford. These have gone into production. Bakken doesn't produce as much anymore, but these two have produced quite a bit. This is what has really fueled our energy independence, if you will. Interestingly enough, if you have been paying attention to what's going on with the price of oil, well, let's go back a few years. This is about 2005. Look at it, it was up to $140 a barrel. I think it actually reached $150 a barrel sometime around 2007, early 2008, somewhere in there, if I remember right. We were paying over $4 a gallon for gas. I don't know if you folks can remember that, but that was the reality. And then boom, it drops off. Well, where are we at now? So again, $140 a barrel. Let's see here if I can find what I'm looking for. That's not it. I have a new price of crude oil. Maybe I can't find it. No, that's the Exxon Valdez. Okay. I'll pause for just a second till sorry about that, folks. Just so many pages open, I am stumbling a bit with those. So here, if you look at, this is from the Energy Information Administration. If you look at the price of oil, it's no longer $150, $140 a barrel. We're down to $24, $25 a barrel, and that's a big improvement. If you remember last week, there was a point when crude oil actually went negative. Now, I don't think anybody was selling it, but they were. If they had, they would actually be paying you to take the crude oil. And there's lots of reasons for that. We'll get into in another period, another class period. But we're in a whole new world. I actually heard that gas in Red Wing was under $1 a gallon. That it was 99.9 a gallon last week at some point. So this is a whole different world than most of your lives, and again, we'll get into some of the reasons for that next lecture. I wanted to finish up today's lecture since we're talking about how much oil do we have, and this notion that we're going to run out. Well, resources resource estimates don't seem to indicate that that's the case. If you look at your notes, crude oil proven reserves, there's proven, probable, and possible reserves. When you read an article about how much oil we have left, look for those terms, and you can look back to here to see what they mean. Proven reserves are what is most commonly referred to, and proven reserves are those that have a 90% probability of being produced at a low estimate. For instance, any oil field will have an estimate of reserves. How much oil is there? Is it 5 billion barrels? Is it 20 billion barrels? Okay, that's a low and a high estimate. So a proven reserve is a conservative number. It's a 90% probability that a well will produce or a field will produce to that low estimate. Pretty good odds that it's going to produce that much. Most fields produce well more than that low estimate. A probable reserve is that field will produce 50%, a 50% probability that it'll produce greater than or equal to a best estimate. A best estimate is, everybody's contributions, all the science, all the gut feeling, all the history they have from nearby fields. What is that best estimate? And then there's possible reserve, 10% probability that well produce greater than or equal to a high estimate. This is the best case scenario. And there's this concept of technically recoverable, what can be pumped, and this is something that has changed through the years. If I still have it up, I'll tell you a little story about this field right here. Those of you in geology have heard this before. This oil well was drilled in 1991. I was on the rig talking to the geologist at site on location at the time. He gave me a bunch of samples, good deal of information, wonderful to talk to him. They drilled down to about a mile deep in the Kansas prairie. They were looking for oil that was right alongside an old ocean reef. So a near shore environment. There's lots of them scattered around Kansas. You got to understand, this is now 3,000 feet in elevation. So plate tectonics has pushed the land up, but it used to be below sea level. And that salt water that's down there is evidence of that, as well as many marine fossils in this area lend strong credibility to that. At any rate, the geologist and his drill crew drilled the hole mile deep. They found what they call show, traces of oil. There was oil there. Problem is, in 91, price of oil was, 19, 20, 25 bucks a barrel, I forget exactly. There wasn't enough oil there to justify pumping it. So they capped the well, poured concrete down it. Well, a few years later, if we go back to that diagram of oil prices, so here's early 90s. A few years later, the price of oil started going up. And so they unplugged the well, and they put a pump on it. It's a low-profile pump so that this center pivot can go over it. And they started pumping oil from there. And so this concept of reserves and recoverability is always governed by things such as the market value of the oil that can come out of it. If the market will pay enough money to extract that oil, they'll put a pump on it. But guess what? With market prices as low as they are, you're not seeing much exploration in the Bakken right now, in the Eagle Ford or Barnett fields. There's not the return, so people are not doing exploration right now, not to the same extent. But that oil's still in the ground, that gas is still in the ground. One of the things, the last line there, reserves located using stratigraphy and seismic testing. I will pick it up there next time with showing you some images of what seismic testing looks like. The idea is, how do you know where to look for oil? Well, it's easy on this map. If I own some land right there, dig a hole, I should find oil. It's not ever that easy. And so we'll consider that technology next time.